All right. Hi, everyone. My name is Vikram. I am a PhD candidate at
Sorry,
the
let me do that. Yeah,
Yeah, sure.
yeah, yeah. So hi everyone. Welcome to today's session. So we have Vikram, who I met in CVPR, and Vikram is currently a PhD candidate at Mila at the University of Montreal. He works on representation learning and generative modeling for images, videos, and 3D. His past projects have spanned video prediction with score-based diffusion models, 3D human pose estimation from images and videos, multi-resolution image generation using continuous normalizing flows. Vikram has also interned with Meta and Google, and also with Unity Technologies. He's also a visiting researcher at the University of Waterloo and an advisor for Blue Lion Labs, a startup working on AI for aquaculture. Nice. So yeah, welcome, Vikram, and the floor is yours.
Thanks, Shashank. So, hi, everyone. My name is Vikram. So, as Shashank mentioned, I have worked during my PhD on basically at the intersection of deep learning and computer vision, more specifically on conditional generative models for images, video, and 3D. So, primarily, I've worked on generative modeling for images using multi-resolution continuous normalizing flows, for 3D using other stuff like diffusion models and so on. And the topic that this talk is going to be about is on video. So we have some work on generating video, not from text, but generating video unconditionally or from the past. That's video prediction, or interpolating the video. So generating the middle frames of a video given the first few frames and the last few frames. So that's interpolation. So we are able to solve all three tasks simultaneously using the same model. So I'm going to take you through how we reached that stage. Are you able to hear me well?
Yes, we hear you well, but we don't see any slide. I don't know if you
Yeah,
are.
I'm just going to
All
share
right, all right.
the slide now.
Okay.
I guess I can share the tab. Yes. I guess you can see this slide now.
Yeah,
Beautiful.
so now we can
That's
see.
perfect.
Yes.
Great, perfect. Okay, so I'm going to be looking at this tab. I can't see the WebEx window if I'm looking at the tab. Shout out if somebody has questions or anything. The way
Okay.
I like to present is that I give pauses in the middle of my explanations so that if somebody has a question, you can ask that question. So feel free to do that in that time. You don't have to wait all the way until the end of the presentation. And the way I've designed this talk is, well, first of all, let me tell you what we've achieved. We use score-based denoising diffusion, video prediction, and generation and interpolation in the same model. And it uses denoising diffusion probabilistic models in the background. And here are a few samples to get you going, just to hype up what we've achieved. The way I've designed this talk is that it's part of a larger talk where I give a tutorial on denoising diffusion models. Let me switch on the laser pointer. So I give a tutorial on denoising diffusion models. I also mention the other alternate formulation, which is score-based generative modeling by Yang Song and all. And I connect these two. And then I give an SDE formulation of the same. And then I move on to MCVD, which is our work. But because we're limited in time, I'm going to probably skip this one and this one. But I'm happy to share the slides with you if you want to take a look at it later. And maybe at the end of the talk, I can go through the slides if somebody's interested. So I'm primarily going to cover a tutorial on denoising diffusion probabilistic models, and I'm going to skip ahead to what we achieved with it.
Okay.
So I'd like to see a show of hands. How many of you are very familiar with denoising diffusion models? Okay,
No
a lot of
one.
people. Good. Awesome. So this tutorial will be very useful for you, I hope. So, denoising diffusion probabilistic models. Primarily, these are generative models. What that means is that we would like to generate new data that looks like the data that it has seen before. So, for example, in this particular case, there is some data, and this is from the data set called CFAR10. So it has cars and planes and like 10 categories of images in it. And what we would like to do is we'd like to make a model that can generate more such images. The way we do that in the case of DDPM is that we hypothesized that we can add noise to these images. So we can progressively keep adding noise to these images. And because adding noise is an additive process, it should be possible to subtract out the noise in the reverse process. So that's the hypothesis. And that's how we're going to proceed with this. There are many other ways to do the same thing. There are many other ways to generate new data given previous data. The particular track that these people have taken is that we can add some noise, and because we're adding noise, we can remove that noise in the reverse process. So the forward process consists of adding noise. We don't just add any noise. We make a mathematical formulation of it, and we say there is a transition probability now from one particular image with some noise added to the next image with noise added to this image. And this transition probability is governed by a Gaussian distribution with a certain mean and a certain variance. The mean being governed by this quantity called beta, and the variance also being governed by this one. The value of beta goes from 0 to 1. I'll explain what all this means. Just take note that this is essentially a Gaussian distribution. So when we sample from this, we sample stuff that looks like this, except that it's a weighted sampling of this. So instead of sampling just this, our mean is some weight of the previous image. So we initially sample just this image multiplied by this weight. And then we add this, an image that looks like this, times the square root of this beta t. So it's a, oops, no, I don't want to leave this. Yeah, can you still see the screen?
Yeah, it's fine.
Yeah. So it's a weighted sum of the previous image and the noisy image. Given this, it is possible to jump directly to this XT from all the way from the data point itself. The data point has no variance in it. The data point is fixed. And because we're transitioning step by step from here to here, and because the transition steps are all Gaussian, it should be possible to jump directly from x0 to x2. So this probability is governed by this. You just have to multiply all the intermediate Gaussian formulations, and you'll get this nice new Gaussian formulation, which is some factor of the previous beta t's that we have. Now I'll explain what this means. So any noisy image xt is a weighted sum of the actual data point x0 and a noise sample epsilon. So epsilon is here used to represent a sample from a standard normal. So it's a weighted sum of x0 and epsilon. Alpha goes from 1 to 0. So at the data point at t equals 0, alpha is 1. So when alpha is 1, x0 is simply x0 plus 0. So at capital T, alpha is 0. So when alpha is 0, x capital T is 0 plus epsilon. So it's simply just epsilon. So it's a linear transformation from x0 all the way to x capital T. Now here's a question for you. So because all this is correct, suppose I want xt minus 1. What would be the formula for xt minus 1? Anybody can shout out if you want.
Yeah, it's the same formula with alpha t minus 1, and it's the exact same terms.
Correct. Exactly. So it's just another weighted combination of the same x0 and the same epsilon. So this is important to note. You can keep an epsilon fixed, and you can get this full trajectory with the same epsilon. Whereas in the previous case, when we were talking about transitions, you needed to sample different epsilons at each step. But in this particular case, you can just sample one epsilon and you get a whole trajectory defined by that epsilon. Right? So yeah, that's absolutely right. Xt minus 1 is root alpha t minus 1 times the same x0 plus root 1 minus alpha t minus 1 times the same epsilon. Now, when I say same epsilon, it's just a matter of choice. Probabilistically, it's the same. I would not get the same xt through transitions as I would get with this one in terms of real pixel values, but probabilistically, it has the same likelihood as had I done transitions. That's all that it means. Okay, so why are we doing all this? We'll come to that. An intermediate step is, so now that we've seen this is how do you extract, how do you estimate xt given x0 and epsilon? I flipped this equation 2 times and I can say, how do you get x0, the data point, given xt and epsilon? So this is what we want, right? Given a noisy image and the noise that has been added to it, I can subtract out the noise and I can get a real data point from it. The third formulation is, how do I get the noise that has been added given the noisy image and the real data point? So these are just flips of the same equation. But I have color coded them because you'll see them later on, and it'll be helpful. Okay, so now we get to the real stuff. How do we reverse this? So suppose we are at xt. So we've come from x capital T to xt, and we want to get to xt minus 1. How do we do that? We can probably estimate that there is a probabilistic way of doing it. So we get pt of xt minus 1 given xt. And so we would want to formulate this reverse probability. We have formulated q of xt given x minus 1, and we want pt of xt minus 1 given xt. So we want to flip the probability. The only way I know of how to flip probabilities is using Bayes' rule. So I'll use Bayes' rule. I'll use Bayes' theorem. So pt of xt minus 1 given xt is qt of xt given xt minus 1 times pt of xt minus 1 by pt of xt. But these two quantities are unknown to me. It's a very complex data distribution for which I don't have a nice compact representation of the probability. So that's the issue here. Right? So I have this one. This is basically the transition probability from before, but these two are unknown. So what do? I do something weird. I say, because these are unknown, let me condition them on the only thing that is known in this whole process. The only thing that is not a variable in this process is x0. So let me condition it on x0 and see what happens. Right? So I add the condition of x0, and now these two probabilities are computable. So this formula is qt of xt minus 1 given x0, which is this transition probability. And this one is qt of xt given x0, which is this transition probability. So this one and this one are also knowns. So now all three are knowns, and we have a compact formula for this probability. So it's the probability of xt minus 1 given xt and conditioned on x0. And you can use your favorite mathematical shortcuts and formulae, and you can get to a compact representation. Turns out this is also another Gaussian with its own mean and its own variance, the mean being captured in this formula and the variance being captured in this formula. But notice now my unknown has shifted from probability of xt and probability of xt minus 1 to x0. And in fact, that is the original unknown. If I knew x0, I wouldn't have to do this whole long winded process from noise all the way to data. Right? So how do I estimate x0? I use the second formula where I say x0 can be estimated if I know xt and I know epsilon. Right? So if I know, I know xt because that is where I have reached so far. And if I can estimate epsilon that has been added to make this xt, then I can subtract out that epsilon and get x0 from the formula that I showed you before. So the second formula that I showed is just a flipping around of this first formula. So if I know, so I'm at xt. If I can estimate epsilon, I can estimate x0. If I can estimate x0, then I can use this formula to sample from this distribution to get xt minus 1. If I know x0, why am I sampling xt minus 1? It's because x0, it's a bad estimate of x0. This is a bad estimate of epsilon. So given just this image, I can intuitively see that it's actually not completely possible to estimate epsilon accurately. So I would get only an approximation of epsilon, but that approximation of epsilon is good enough to give me an approximation of x0, and that approximation of x0 is good enough to then add noise to get xt minus 1. So now the problem is, how do I get epsilon? Right, so we've been shifting goalposts all over. Estimation of epsilon is done by a deep neural network. So this is where machine learning takes over. So until now, it's been following probabilistic mathematics specifically, but now we get to machine learning. So estimation of epsilon given xt is done by a neural network that has been trained for that task. How do we train it for that task? Basically, we take an x0, we sample an epsilon, we add them together in a weighted fashion to get xt. We feed this xt to this network called epsilon theta, parameterized by theta. We get the output, and we have a reconstruction loss on the output of the network with the original epsilon that was added here. Right? So this is just a basic reconstruction loss, a mean squared error, between the estimated noise and the actual noise that has been added to make xt from x0. So we get x0, we sample an epsilon, we get xt, we feed this xt to this neural network and also the level of noise that has been added, and we get an estimate of the noise. We have a reconstruction loss on the noise, and we backpropagate through the neural network. This is how we train the neural network. Given this trained neural network, and we train it on like different values of epsilon with different values of x0 and different values of the noise level. So these are the three variables in this. The way we handle the variables is we just do boosting. We sample random values of each of those parameters, and we take an average across all. So it's an expectation over the noise level and the data points and the noise images. So given this formulation, it's complete now. So we are at xt. We feed xt to a neural network to get an estimate of the noise. Given this estimate of the noise and xt, we get an estimate of x0. Given this estimate of x0 and xt, we get an estimate of xt minus 1. So practically what we do is we go from xt all the way to x0, and then we come back from x0 to xt minus 1. So what we're doing is we come back all the way to the start to get an estimate of the clean data. Then we noise it up, but with lesser noise than what we started with. And so we do this formulation repeatedly, and we eventually get to x0. And the reason we do it in this fashion instead of just stopping at x0 is because epsilon theta is not an accurate estimate of epsilon. It is not possible to get a completely accurate estimate of epsilon. That's why we're having to noise it back up again and then go back and then noise it back up again and so on. Any questions so far? So this is how denoising diffusion models work.
Hi, this is Magnus from online. I have a question. Is capital T a hyperparameter? How does it affect the reconstruction?
Right. So capital T is indeed a hyperparameter. When they had started, I think some people used 1,000 steps. So capital T is 1,000. Once they figured out that this formulation works really well and they wanted to make it even better, a team at OpenAI made it 4,000 steps. So it's really a heuristic. It's up to you. It's your choice. We have found that you can train with 1,000 steps, but then when you're sampling, you can skip a few steps and sample a total of, let's say, 100 steps, and you're going to get good enough results with that. So at this point, as far as I know, it's an empirical evaluation. There's no particular heuristics to that. Intuitively, what it means is that if you take smaller and smaller steps from noise to data, you're going to get crisper and crisper end result. And that's because the noise you're estimating at every point is a bad estimate of the noise. So the more steps you take, the more you're compensating for the badness of your epsilon estimate.
Okay, thank you. Very clear.
Hey Vikram, I have a very naive question probably. So to estimate epsilon theta, they just use a normal autoencoder, or what is normally done? What is the deep neural network that is used here?
So to estimate epsilon, traditionally people have used a UNet. So it's not an autoencoder as such. I understand that it's an autoencoder formulation. So you can think of it that way. It's not a variational autoencoder. You can think of it as an autoencoder. But the difference between an autoencoder and a UNet is simply that UNet additionally has skip connections. So it's an autoencoder with skip connections from the encoder to the decoder. So that's the network they use. The reason they use that network is because so this particular problem is like that of semantic segmentation, where the input and the output have the same dimensionality. So the input is an image, the output is also an image. And a unit has worked really well for the task of semantic segmentation, where that still continues to be true. The input is, let's say, a map, and the output is the segmented output of where is a tree and where is a park and so on, right? So that's semantic segmentation. So a unit has been very useful in these sort of tasks where the dimensionality is the same, but you need to extract the right kind of features from it to get the right kind of output. So they used a unit. And there have been
So
innovations over the unit after that.
right. So I think the problem with having skip connections if the input image is not so complex is that the reconstructed image like very easily tries to just become the input image because of the reconstruction loss. So I mean, has it been the case here? Because the skip connection actually work well when the input image is a bit complex, but when it is as simple as a noisy image, I think it can easily reconstruct it, right?
Yeah, but in this case, the output is not trying to be the input. The output is trying to be something else. So the input is a noisy image, but the output is the actual noise itself.
Okay, input is a noisy image. Okay, I got it wrong. Okay, fine. Sounds good. Yeah, cool. Thanks.
Another alternate formulation is the input is the noisy image, but the output is the clean image. So you can either estimate this noise, or you can say, I'm going to skip all this math and just directly estimate the clean image itself.
Right.
So that's an alternate formulation. People have used that. Practically, they have found, well, some people have found that particular estimation to be more better to generate cleaner images, because the hypothesis is that it's a unit, it has convolutional layers in it, so it is more it's more beneficial for things that look like images. A noisy image does not look like an image because it does not have any spatial correlations, whereas a clean image is an image. So estimating a clean image is easier than estimating noise using convolutional layers.
Right. Yeah, sounds good. Thanks.
All right. Well, if there are no other questions, I can proceed. Oh, yeah, go ahead.
Yes, so epsilon theta is not an accurate estimate, but as we move closer and closer to the original image, does it get like more accurate? Because I guess since we get closer to x0, it should converge somehow to the real epsilon. Is this
correct? You can say that, and that's because, well, I mean, I would say it's the other way around when you're estimating epsilon, because the further and further you move from the original image, the clean image, the more noisy your image looks. So the easier it is to estimate the noise in that image.
Okay.
Right? It's the other way around when you're estimating the clean image. The closer you are to the clean image, the easier it is to estimate the clean image.
Okay.
So yeah, indeed, it is easier to estimate the noise at certain levels of noise than others. And that is why we have to average out the weights. So we have to compensate for that easiness or difficulty in estimating the noise at different noise levels. And so we multiply a factor to equal out the loss levels at every noise level.
Okay, thank you.
Yeah, great questions. I'm extracting details out of the original papers that I have not included in this particular presentation. Yeah, so, very good. All right, so if there are no more questions, I'll proceed. Sure, okay. All right, so given this formulation, yeah, you can just add a for loop around it and you get the sampling technique. So you start with xt, which is sampling of pure noise, and then in a loop, you take multiple steps to reach all the way to x0. And so denoising diffusion probabilistic models contain essentially two steps, independent of each other. The first step is what I call noise matching, which means that you're trying to reconstruct the added noise to your input. And this is the stage of training. So the only training that you have is here. You're training an epsilon theta network to estimate epsilon given different values of t, xt, and epsilon. Then once you have a trained network, you do generation using this combination. And that's essentially how DDPMs work. You can think of text-to-image models as adding an additional condition of the text image. Everything else remains the same. So you train it on different text-image pairs now. And the generation is exactly the same. You just additionally condition this network on whatever text you want at each stage, and you then get an image that corresponds to the text. You can replace text with any other modality, and you get different conditions. Like I mentioned, the alternate objective here is, instead of estimating epsilon, I can just estimate x0 directly. And in some cases that has worked well. It's still the same formulation, it's just a reconstruction loss on x0 and expectation over the different noise levels and different x0s and different noise samples. And there's a for loop around it, so you can do that. So a lot of the more successful denoising diffusion models use the alternate. So for example, DALI2, image and stable diffusion, all of them use this particular objective and not the original noise matching objective. There are alternate sampling techniques as well. So for example, well, this one is DDPM. We know how this works. But you can see that this particular step is essentially noising x0 all the way to xt minus 1. We know how this works. We have seen that this is our original cumulative transition probability, right? So instead of using this complex equation to do this particular sampling, let me just use the original sampling, right? And so this particular sampling technique is called DDIM, Denoising Diffusion Implicit Model. So given this, now you can backtrack and say, oh, okay, let me find the original probabilistic math to explain this, and so that I can get this as the correct sampling technique. So you then go back and tweak your equations, and you get, and you formulate a theory around that. And so if you read the paper, they start with the theory. They say that the original probabilistic distributions are not the ones that we're considering. We're considering an alternate probabilistic distribution, which eventually give us this particular equation as the sampling equation. And so this is much simpler. And this is a paper called DDIM. By the way, for whatever papers I'm telling you, I've added links to the archive versions. Yep. The good thing about this is it's deterministic. You don't, when you're going from x0 to xt minus 1, you don't add noise anymore. Instead, you use the same epsilon that you had estimated earlier to add to this to x0 cap. You can have a stochastic formulation for the same thing. Again, and when you want to make it deterministic, you just turn this off. You say sigma t is 0. I'm not going to go through this one. So now there are several expansion packs from this. So you can imagine that, so given that this is the baseline, this is the baseline model that you start with, you can cascade multiple denoising diffusion models. You can have one denoising diffusion model that generates an image at 32 by 32. The next one is conditioned on that image to generate the next image at 64, and so on and so forth. So you can do super resolution. You can do denoising in latent space. What that means is that instead of operating in the image space and noising up images, you can noise up latent embeddings. So you can first of all embed your entire data set into an embedding space and only operate in this embedding space for your entire denoising, for your entire diffusion, and then decode it back to the image space. So that's what these papers do. I'm sure there are loads and loads of more papers that have come up since then that do this. You can also add non-Gaussian noise. So for example, in our formulation, we've only added Gaussian noise, and we've seen how convenient the equations get. But instead of Gaussian noise, you can think of adding gamma noise, Poisson noise, and so on. And you have different formulations. You can think of faster sampling techniques. So I've only shown you two, DDPM and DDIM. But you can think of better and faster sampling techniques. There are loads and loads of papers on that. And finally, there is a concept called classifier guidance and classifier free guidance. What this means is that, so we would like to generate an image, but we know that that image is the image of a dog. So in training, we condition on the dog, And then while sampling, we also condition on the dog and we get the image of the dog. That's one formulation. But what we would like to do is, suppose we don't have the classifier. Suppose we don't have a formulation, the conditional input itself. Or we have the conditional input, but we would like to use the same DDPM formulation. What we can do is we can do something like what conditional GANs did. And when the image is estimated, you also feed the image to a classifier. And that classifier then classifies whether it's an image of a dog or not. So then you have a model that is universal, that is unconditional, but it helps image generation by having a classifier at the end that predicts which class it is. So then there's a guidance provided to this unit to estimate the noise based on the class. Now, that is classifier guidance. Now, suppose you want to use this formulation, but you don't want to use the classifier itself. So what people did is they feed the class as a condition, but only half the time. So half the time you have the condition and half the time you don't. So for half of the samples, you're training your model unconditionally, but for half of the samples, you're training your model conditionally. So then, because you're training it up, packaging it across batches, your model is now able to handle the case where there is no class, but take the help of class when the class is available. So that is called classifier-free guidance. And there are many more techniques, and usually the denoising diffusion models of today have a combination of these, to help them perform better. So these are a few expansion packs from here. I'm gonna skip score-based generative modeling, and I'm gonna jump to MCVD, but I can come back if people are interested. So, so far, any more questions before I proceed? Yep.
Is there a link with normalizing flows? Because I feel somehow it's the same. We have a latent space, and we are, except here maybe the latent space has to be the same size as the original. Well, it has to be, yeah, because it has to be inversible anyway. But I mean, like, yeah, what is the link? I'm sorry, it's sort of non-formal question.
No, yeah. But so this is the type of question that deserves a discussion. So let's see. So normalizing flows. In my head, there are two kinds of normalizing flows. There are discrete normalizing flows and there are continuous normalizing flows. If you're talking about discrete normalizing flows, well, do you know how discrete normalizing flows work? Like when I say discrete normalizing flows, they're the typical normalizing flows.
From what I understand, we want to get so we start from a noise like distribution, for example, Gaussian distribution, and we want to get close to the distribution of some natural images.
Mm-hmm.
And we do this by some inversible transformation.
Mm-hmm.
And it made me think, well, this noising, it looked a bit like this transformation, but the inverse of it, I guess.
Mm-hmm. Yes, so exactly. So in your inverse, in the normalizing flow, you are constrained to use invertible transformations. So it follows kind of the same properties where you start with data, you go to noise, or you start with noise and go to data. And you do this step by step, decreasing the noise little by little. But each step is governed by an invertible transformation. Here, that's not the case. It's not necessarily an invertible transformation because there is a notion of a variance in our DDPM formulations. So it's not strictly invertible. You can estimate a different denoised image for the same noised image. And in fact, you can sample multiple different denoised images at each step for each noised image. Whereas in a normalizing flow, if you start with one noise image, the entire trajectory is predefined.
Yes.
Now, this sort of formulation of predefined trajectory from noise to image in the case of normalizing flows is a constraint, but it is a good constraint in the sense that now you have fixed trajectories from noise to data, The only problem with that, and I have some experience with normalizing flows, so I'm just drawing from that experience. I'm talking to a lot of people who worked on normalizing flows, is that first of all, the intuition is there need to be trajectories from noise to data in the first place. So if you have a distribution of images and you have a distribution of noise, there needs to be a one-to-one mapping between a noise point and a data point. If this one-to-one mapping is not even possible in the first place, there can never be a normalizing flow that connects them. That is not the case with DDPMs or denoising diffusion models. Two, if there is a one-to-one mapping, it is a highly constrained mapping. So you need a highly capable neural network to discover that mapping. Therefore, the best normalizing flows are those with a large number of parameters. You see, OpenAI and all those OpenAI cool models that perform really well on faces and stuff. First of all, they perform really well on faces because faces are symmetric and they are a much easier image distribution. Whereas if you go for images like from ImageNet and your favorite large data set, they're much more difficult to find. Two, they are huge. So the number of parameters like that time itself was like 2 billion or something. So they're huge models. Whereas DDPM and other denoising diffusion models are not as big because they don't have this rigid constraint of one-to-one mapping and non-intersecting trajectories. Two, so now if you go to continuous normalizing flows, do you know what continuous normalizing flows are, by the way?
No, I'm not sure. Is it like turning this into an SD or like something like this?
Correct. So, but the problem is you can't convert it to an SDE because you need invertible transformations. Therefore, it is only constrained to an ODE. So the trajectory from data to noise and noise to data is an ODE. And because it's an ODE, it's invertible. Right?
Okay.
But again, because it's an ODE, you're assuming that there exists an ODE that can connect the data distribution to the noise distribution. If such an ODE exists, then the function of that ODE must be very powerful. Because that function needs to be very powerful, your neural network that models that function has to be really big. So the same disadvantages follow. Very good observation. So I can now mention that the DDPM formulation can also be modeled in the continuous domain. So what I'm showing you so far and what I will show you from now is in the discrete domain, where we have discrete steps from data to noise and discrete steps from noise to data. But it can be formulated as a continuous process using stochastic differential equations. Now you turn off the stochasticity in those stochastic differential equations and you get ordinary differential equations. So you do have an ODE and an SDE formulation of denoising diffusion models. And yet they are more powerful than continuous normalizing flows.
Thank you very much.
Any other questions? All right. So let me...
Can I have one online Max again? I assume that when you estimate the noise, the output will not be normally distributed. Then you try to do any whitening when you generate in the generation step, because the only constraint is implicit when you train the network, right? To make the output and normally distributed.
Could you repeat that? So in the in the noise to data process or data to noise process?
In the noise to data.
Mm-hmm.
So you run the network every time, and it gives you an output which would not be, I assume, normally distributed strictly.
I see.
So would it help to try to make it more white or something like this?
It's an interesting thought, but I would say no. And the reason for that is that you're training with a reconstruction loss. So you can say that, yeah, sure. So at the last layer, whatever output you get, normalize it, and then have a reconstruction loss on that normalized output because white noise is normal. That's not strictly true, though, because most of the samples that you get out of a Gaussian distribution do not have mean zero and variance one. Yeah, there is this theory. I forget which one. So there was a paper in 2015. Anyway, it comes from information theory and measure theory that when you have, let's say, a 2D representation of a Gaussian with the center being the mean and the variance being, let's say, 1. When you actually sample from it and see where the samples are coming from, the samples don't come from that point at the center and with variance 1. Instead, they come from a ring, a little radius away from the center. So all those most probable samples from the ring, they don't have 0 and variance 1. So I would say it may not help to normalize the output estimate of the noise.
Thank you. Very interesting.
All right, any other questions? Okay, so let me proceed to MCVD. So this is a paper that was published at Neuro. Basically, what we want to do is we want to solve video prediction, which is given one frame of the past, what are the frames in the future? Generation, which is what are the frames of a video unconditionally? And interpolation, which is what are the middle frames of a video given the first frame and the last frame. So how do you get to video generation? How do you expand from images to videos? Simple, you just replace your X being images with X being the video. Right? So let's say you have a video of 5 frames. So you now, instead of estimating 1 frame at a time, you estimate 5 frames at a time. So estimating 1 frame would have been estimating images. Generating 1 frame is generating an image. Generating 5 frames is generating a video. So you just generate all 5 frames simultaneously. And you train it with the same objective that you had before. Right? Easy. But how do you solve video prediction? You solve it by saying, okay, in addition to your XT and your T, I will also condition the neural network on the past frames. Simple. Just as I would have conditioned on text or some other modality, in this particular case, I'm conditioning it on past frames and trying to generate all 5 frames of the video simultaneously. And so I train it in that way. I sample P comma X0 as my data. So P being past frames and X0 being the future frames of those past frames. So I sample them at once. So for example, let's say I have 2 past frames and 5 current frames. So I will condition on these 2 past frames to generate 5 current frames. And the formulation for interpolation is I have both past and future frames that I'm conditioning on. And so I'm sampling P, X0, and F. So past frames and current frames and future frames at once. I'm conditioning on past and future frames to generate the current frames. And this is how I train it on all 3 individual tasks. But these are 3 different loss functions for each individual task. So I will, if I were to train on these, I will have 3 different models, one that solves prediction, one that solves generation, and one that solves interpolation. How do I have one single model that can do all 3 simultaneously? So yeah, can we do better than this? Turns out the secret sauce is random masking. So what we can do is, suppose I have a model that performs video prediction. So while training, I condition on the past frames and I generate current frames. Now, to perform video prediction plus video generation, I not only use the past frames, but I also have a mask on that past frames. So what this mask means is that I sample this mask from a binomial distribution. What that simply means is that I sample either a 0 or a 1. So, and I multiply that 0 or 1 with the past frames. So for some samples, a 1 is multiplied with the past frame, so I do see the past frames. But for other samples, I multiply a 0 with the past frame, so I don't see the past frames. So in a batch, I might have some samples that are conditioned on past frames and some samples that are unconditional. Therefore, the model is simultaneously trained on both prediction and generation. And so on with interpolation, I do the same thing. I have 2 masks, one for the past frames and one for the future frames. And so I multiply the past mask and the future mask independently. And so quarter of the samples have both past and future frames. Quarter of the samples have the past frames but not the future frames. Quarter have the future frames but not the past frames. And quarter have the unconditional frames. And so this model is trained on all 3 tasks of prediction, generation, and interpolation, and on a task of like past prediction. We don't really use that task. So this is a model that can be trained on all three tasks simultaneously. And the secret here is random masking. So we randomly mask out the past and or future frames in every batch. And so you can sort of estimate, sort of have a visualization of it like this. So we have video prediction, video generation, and video interpolation. But all three simultaneously happen when we can mask out the past and future frames. And all two can happen simultaneously when we're masking out randomly the past frames. Now, how do we generate longer videos? Because we have past frames and we generate 5 frames at a time. We do some sort of a teacher forcing where we say, okay, let's take the last 2 frames, consider those as the past frames, and then generate the next frames, and so on. So we have long-term video prediction with this. Even though we're training it to generate 5 frames at a time, it is possible to generate 30 frames or 50 frames or 100 frames. Of course, as you keep going longer and longer through time, the frames will be lesser and lesser correlated with the past frames. So then they may not look as realistic as they would have at the initial stages, but it's still possible to generate long-term video. To improve the video quality, you can additionally condition on the original past frames at every generation. But that's all. That's all. That all can be done. People have done that as well, so it works. If you look at our paper, we have what was then actually I think it's still state of the art, especially on cityscapes with like 128 by 128 images. We have state of the art FPDs. So we tried this out on multiple data sets. So we started from small and went larger. So we started with moving MNIST, essentially a data set of MNIST digits moving around. In fact, we started with stochastic moving MNIST. So the way the digits move around is stochastic, so you can't really predict them by an ODE. So we started with that. Black and white, just numbers moving around in a screen. Then we had KTH, which is humans, black and white humans jumping up and down, waving their arms, and so on. Then we had Bear, which is a robotics data set, colored images, but in a constrained environment where all that's moving is a robot and it's moving different objects in its vicinity. And then we have Cityscapes, which is a self-driving data set in Europe, and we have essentially a car moving around in Europe, and we're supposed to predict the future frames given the past frames. And then we also tried it on UCF, which is essentially YouTube videos curated according to some categories. And we had good results there as well. Not as good as we hoped, but some good results. The important point to note is that compared to other works, so for example, all the other works from, let's say, big companies or people with more and more resources than us, have been able to train on, let's say, 15 frames at a time. And in fact, their evaluation is on 15 frames. So they should have done better on these 15 frames that they're predicting. But we predict only 5 frames at a time. And we then elongate that using autoregression and get 15 frames. And still we have better results than the previous works. So it's a very powerful method. You can use it for long-term prediction. And even though it's trained on fewer frames than comparable models, it can perform better than the comparable models. Here's an example. So you can see that in the past frames, there is an arrow that is a little car, and it's coming closer and closer, and it goes underneath the car as well. So it's one of our favorite examples from this, where you can see that it's actually not memorizing anything, but it's in fact able to learn how objects are moving in the scene. Yeah, here are a few examples of interpolation. A few examples of unconditional generation and prediction. And that's it. Any questions?
Yes, please. Thank you for the talk for now. Can you detail what spatin and concat mean on your models, please?
Oh, sure. Yeah. So let me turn on. Oh, sorry. Okay. Turned off sharing. Yeah. So I do have that, but I skipped the slide. Let unskip it. Okay. So the architecture of the model is as follows. So this is the core. So this is the core, which is the unit. So the input to the unit is noisy current frames, xt, and the output is the predicted noise, epsilon. You use this epsilon and this xt to denoise, and you get denoised current frames xt minus 1. And in the original formulation for sampling, you just feed this xt minus 1 back as the new xt, get the epsilon, denoise, feed this back, and so on. Okay. During training, you feed xt as x0 plus epsilon, and you sample epsilon at some noise level t. So during training, you sample t from a uniform distribution, but during sampling, you sample t from capital T to 1, or 1 to 1 by t. So you have this noise level. You get x0 and epsilon, and you get xt, and you feed this to the unit. The unit is also conditioned on the t, and you finally get epsilon theta. For our formulation, we have to additionally condition on the past and future frames, or a masking of the past and future frames. So the way we do that is, first of all, we have the past frames and the future frames. We just concatenate them together and feed this as additional conditioning. I'll tell you how we do the additional conditioning. And these past frames or future frames are given by the actual past frames masked out and the actual future frames masked out. So this is the final condition that we feed it in. Now, how do we condition the residual block on the conditional frames? We do that using a block called spatin. So if you expand this residual block, it looks like this. So there's a group norm, and there is some conditioning information from your noise level that's fed in, and there's a convolution layer, another group norm, conditioning, convolution layer, skip connection, and you have the output, right? Now, the group norm itself is, a normalization. So the way it works is it takes the input feature, it normalizes it, and then it denormalizes it, and then it pushes it forward. The denormalization parameters are estimated by another neural network, which is our pattern block, conditioned on the past frames and future frames, the conditional frames. So this is similar to another method called SPADE, which is, I think, Spatial Adaptive Instance Norm by NVIDIA. So this is from a paper called GALGAN, I think. The paper itself is called SPADE, and the GAN that they used it on is called GALGAN. So it's similar to that in the sense that it contains the same idea of normalizing and denormalizing in the normalization layer, but the denormalization parameters are estimated by the conditional input. So the pattern block itself is pretty simple. You just take the conditional input, you interpolate it to the correct size at that stage. The feature sizes are different, so you interpolate it to the correct size. You have additional convolutional layers, and then you have two branches, one that estimates the scale of the denormalization, and the other that estimates the offset of the normalization. And so you feed the scale and offset to the group norm. The group norm normalizes and then denormalizes using this estimated scale and offset. And the second group norm also does that. There's a second pattern, and so on. Otherwise, if you don't want to use this pattern block at all, you can just simply feed this conditional frames, concatenate them to the noisy frames, and you still have the, you resize this conditional frames, or you have one additional convolutional layer here that resizes them. But essentially, you feed this conditional frames to the noisy frames itself, you concatenate it with XT, and then the rest of it goes as usual. So those are the two variants that we have, using this pattern block and using concat.
Okay, thank you.
I also have a question, maybe more of a curiosity question. You showed that you managed to learn on less data, basically. How big of a computing process did you need to train it?
Right. So for that, I'll go to the paper. So in the appendix, we've given all the information of what are the different computational resources that we use. Can you see the paper?
Yes.
So this is on archive. If you go all the way down to the appendix, we have a helpful table here. So these are the computational resources that we use. So each individual data set, each variant, the number of parameters in the model, the memory that we used on CPU, the batch size, the GPU that we used, the GPU memory that we used, and the number of GPU hours it took to reach the best iteration. So overall, the maximum number of GPUs we used was like 4, each being of 48 GB. So the maximum memory I think we used was like 145 GB. But really, we used about maximum of 100 on average for each of the data set. And in fact, for cityscapes, it was just about 100. Yeah, so 100 GB maximum with the batch size of 64 at different image sizes. So cityscapes was 128 by 128. There was 64. KDH was 64 by 64. Stochastic moving MNIST was also 64 by 64.
Okay, thanks. I look more into it by reading the paper myself.
Sure. Yeah, so we did not use like TPUs or 100 GPUs across like weeks and weeks. I think the maximum time that it took was 4 days or 5 days on the biggest data set. For cityscapes and other stuff, I think it was much lesser time.
It's pretty impressive performance.
Yeah, and our code is open source, so you can download it and use it yourself. I've also open sourced the data, so the exact data format that we use. So there's some pre-processing that we did in order to speed up data loading. So I essentially pre-processed the data and stored it in an HDF file. So I've publicly made them available as well. So you can download the data, download the code, run it yourself, or you can even download the model checkpoints and run them yourself.
Okay. Thank you very much.
Vikram, I have basically a question about the interpolation stuff that you talked about. So this is only specific to moving MNIST. So if I understand correctly, like you have 2 frames where the 2 images, 2 numbers are here and here, and you want to interpolate and you want to generate frames that just interpolate between them, right? So I think my question to you is, how do you compare it with methods that do just simple latent space interpolation to kind of generate these kind of intermediate frames? I'm pretty sure that you must have like come across them. So yeah, could you like share any? Because what they say is that if they want to interpolate between 2 images, it is best to take like the shortest path and the smoothest operation and things like that. So have you observed any kind of weird artifacts, and how did you kind of control them in your book?
Right. So there is a difference between the interpolation that we are doing and the interpolation that those methods do, because those methods are essentially latent methods. They operate in a latent space. They have one latent embedding for, let's say, the initial frame, one latent embedding for the final frame, and then they do an interpolation in the latent space and then decode into the. And what you mentioned was the interpolation need not be the shortest path. It need not be the straight line between those 2 embeddings. It has to be a spherical path. If you take a spherical path that is more visually aesthetic, we are not doing latent space interpolations at all. What we are doing is we are explicitly reconstructing the middle frames. So we are training it to explicitly reconstruct the ground truth middle frames, interpolated frames. And so in sampling, we are explicitly sampling the frames themselves. We are not interpolating in latent space. Our model itself is generating the interpolated frames in one shot.
Okay. Oh, I see. It generates like 3 frames in one shot. That's what you mean. Okay. Then okay, that's different. Okay. So you not go frame by frame, but generate like all the intermediate ones in one go. Okay, yeah, fair enough.
So in fact, one of the works that came concurrently with us, I think, so what they did was, for long-term video generation, instead of generating every frame or every batch of frames, they generated every 10th frame. So you have a model that's trained to predict every 10th frame. So you have a model that predicts the frame 100. And then you use an interpolation model to interpolate in between every 10th frame. So then you have 100 frames, but using 2 models, one that predicted every 10th frame and the other that interpolated between every 10th frame.
Okay, yeah, that's nice. Cool, yeah, thanks.
Any other questions?
here in the room? I guess we're done here. Okay. Online, some people have questions.
I don't see any in the chat either.
I don't see any hand raised. Well, there were a lot of questions during the talk. So you covered a lot of things. And thank you very much for this very interesting and surprisingly complicated but nice talk. It's very, very nice. The power of that is just amazing. Thank you very much for presenting all this work, and I think we have a much better understanding of all that process. Thank you very much, Vikram, and the guys. See you soon at the next seminar. Be careful for the cold over there.
Yeah, thank you so much. Yeah, thank you for having me. This was fun. I enjoy giving these talks, and it's interesting to see all the questions that come up and if I'm able to answer them correctly or not. I hope this was very useful for you.
Yeah.
Yeah, thank you so much for having me here.
Thank you. Thank you.
Thank you so much.
Bye bye.
Thanks a lot, Vikram. Yeah, see you.
Bye-bye.
Thank you very much. Okay, see you. Bye. Thanks a lot.
I think stop recording before switch off it.
Boom.